Oh, hi there. Thanks so much for showing up for your learning. Y'all have your handouts from Monday? Great. So let's take a look at, we're going to be using the number line and solving polynomial inequalities, particularly algebraically. So we're going to look at, we looked at graphically yesterday. Today is algebraic. So let's go. We are going to get an opportunity to review factoring degree 2 to 4 polynomials. Hooray. So lots of practice in delta math, lots of practice in your textbook today. So here are our steps. Did I copy these steps down on the handout, Kenzie? Yes. Do you have these steps there?
I have them written in my app.
Okay, great. So just like solving an equation with these higher order polynomials, we set one side equal to 0. You fully simplify it. You're going to, if that's a rational function, you want to simplify it as well. It's also still useful. And then we're going to order the zeros, any asymptotes, any holes from least to greatest on a number line, and investigate each space in between each one by one. And we're going to check all the intervals between the values from here using an interval chart. Okay? And then we're going to write the intervals that satisfy the inequality. So, if we wanted to look at something like this, we could say, okay, I'm going to just say f of x, just for ease of use, is equal to that function, and it's always, we want to know what values of x make this thing greater than or equal to 0. Well, we can do this algebraically by identifying where our zeros are. I know that when x equals, there's 3 values, no one has yelled them at me yet, f of x equals 0. What are the 3 values? Great. Excellent work. So now we're going to just put those on a number line here. So I got 0 over here, I've got 3, I've got -2, and I've got -8. All right? So I know that this thing crosses the x-axis at those x values. So it's going to possibly, maybe one of them's a bounce, but it's going to possibly change its value and go from negative to positive or positive to negative at those points. So I can test different values and find out what happens for those different points. Let's test f at -10. Okay, so at f at -10, I would have -2 multiplied by -8 multiplied by -13. That would give me a negative value. So it's negative over here between -infinity and -8. Then I test a value from in here. -5 looks good. Let's test f at -5. Okay, so I'm just going to test it up here. That will be 3 multiplied by -3 multiplied by -8. Ooh, 3 times -3 times -8 is positive. So I am positive in this whole region here. Did you notice that I chose really easy values to work with? I could have chosen -pi. -pi is also in that region, but it would be harder to work with. So go easy on yourself. Now, I put on 0 there, but that was just for my own reference. I don't need 0. It's not part of like the points where the function changes. I am going to choose f at 0 to test because, hey, that would be real easy. Okay, at f at 0, we are a positive times a negative. That will give me -48. That's pretty darn negative. So I'm negative in this region here. Okay? And then from 3 on to positive infinity, I might test like, say, f at 10 or something like that. And that would give me 18 times 12 times, ooh, that one's positive now, 7. 18 times 12 times 7 is too huge for a human calculator to calculate, but it sure is positive. So I know that that's positive over there. So this tells me all the intervals where it's positive and where it's negative. So I can now answer this. and I can say this is true, and I can do intervals or I can do inequalities to notate this, and I can show it on a number line as well. This will be greater than or equal to 0 between -8 and -2 inclusive, because we were greater than or equal to. Okay. Or I am also positive from 3 on. So the union with 3 to positive infinity, this function is positive. Now, are any of you feeling like, but I could have just done that by graphing, and I'm good at graphing? Good. Know how to do things 2 ways, and you're better at it. Okay, you might forget how to do it by graphing later on, but if you have 2 things that you can remember, that's better. Also, some problems call for the screwdriver, some call for the hammer, and others you can use either one. So you need to know how to use both to be a good carpenter. Or if you're a good mountaineer, you can climb the mountain on the south face and the north face. It doesn't matter. You can do both faces. You want to be a good mountaineer, a good mathematician. So graphing, I would do this by saying, well, I know that this thing crosses at 3, at 2, and at -8, and its end behavior is such that it would look like this. So I know that it's positive all the way over there and positive in this little region here. That's what it would look like graphing, and yes, I agree it's faster, but no, we want to know how to do this. You just find your intervals and then test 1 point within your interval. That's how you do algebraic. Let's go. So, this one. Oh, it's a quartic. How nice. What's my end behavior here for this quartic? If you were to, yeah, so some of you are showing me the correct dance. We are doing this dance with this quartic. It's Q2 to Q1 behavior. So that's going to help us test our answer. I do know that this thing crosses the x-axis at -5, -1. This one's been written in a weird order. 1, positive 1, that one's 1 there, and 2. Okay, so I might space that out a little bit to give myself some room to work in. 2. And I'm going to call this thing f of x for argument's sake. It just helps my notation a lot. And now I'm going to choose some values to test. Let's test f at -10. So its behavior before infinity, I expect this is going to be positive. I'm going to have -5 times -12 times -11 times -9. 4 negatives multiplying is like flipping a light switch 4 times. It's back to positive. So this is surely positive over here. Between -5 and -1, -4 looks fine to test. Let's do f at -4. So I'm just going to go ahead and test those over here and test it factor by factor. This would be 1, this would be -6, this would be -5, and this would be -3. I have 3 negatives multiplying. That's negative. Okay. Between -1 and 1, I do expect, oh, and then I have 2 here. This is 2. Between -1 and 1, let's test f at 0, because that's easy to test. And I have 5 times -2 times -1 times +1. That's 2 negatives multiplying. And 2 negatives multiplying is positive. And then between 1 and 2, between 1 and 2, we got to use a fraction. We have to use a fraction in here, so I'm going to choose the easiest one to work with. F at 1.5, 3 on 2. Okay, f at 3 on 2. So 5 plus 3 on 2 is positive. 3 on 2 minus 2 is negative. 3 on 2 minus 1 is positive, and 3 on 2 plus 1 is positive. So because here I have a single negative and then 3 positives, I will be negative. But don't I need the actual value of those numbers for each factor? Nah, I just need their sign, right? Here, I'll give you the values. 5 plus 3 on 2 is 6.5, so that's 6.5. This one is minus 0.5. This one is 0.5. and this one is 2.5. There. So you see, one negative. It's negative. And then after 2, let's just test f at 10. You could do f at 100 or f at 1 million if you like, if you want to get your Austin powers on. We've got 15 multiplied by 8 multiplied by 9 multiplied by 11. Of course, all the factors are positive past f at 2. So this is positive. Okay. So now, I want this thing to be less than 0. So where is f of x less than 0? In this region here and in this region here. Okay, non-inclusive because we're not including. So I have here minus 5 to minus 1, and the union of that with 1 and 2. Okay, that's interval notation. I could also say minus 5 is less than x, which is less than minus 1, or 1 is less than x, which is less than 2. Okay? These would be the other ways that you could show these with inequalities. Okay? Fun. Cool. Let's carry on. How about this one? What degree is my polynomial? Is that you're raising your hand to tell me, or are you showing me the answer? Good. Both. Yes. What's the answer? This is a degree 5 polynomial. It's got 2 special roots. They bounce. Just like, never mind. Okay, so I know that this thing is a degree 5 polynomial. It's got 1 cut root and 2 bounce roots. So if we prepared a little sketch, it would, and my leading coefficient is positive. So I know that this thing is Q3 to Q1 behavior. It's going to come up from negative infinity, bounce at 8, bounce again at 7, and cut at 5. Something like that. Negative 8, negative 7, and negative 5. Okay? So that's what it's going to look like. Where is this thing greater than or equal to 0? Well, I can tell you that when x is equal to 8, negative 7, or greater than negative 5, this thing is going to be greater than 0 or equal to 0. Okay? And we can see that very quickly by graphing. If you do an intervals, interval is going to work exactly the same way. You're going to have minus 8, minus 7, minus 5. Test your f of x for different values. And if I test back here at minus 10, I have, this one is useful to look at. Like let's say I look at f at minus 10. You have to do the algebra here. This is always positive, the minus 10. Sorry, this factor, because it's a square. So minus 10 plus 8 is minus 2. Minus 2 squared is 4. That's positive. Okay? This one's now negative, okay, because that's negative 5. And then minus 10 plus 7 is minus 3. Minus 3 squared is positive 9. So we're positive 9 there, we're positive 4 there. We have one negative, it's negative over here. Okay? In between here, it's still negative. And I could test one, but do I really want to? Yes, I really want to. Okay, minus 7.5. Let's test f at minus 7.5. Okay, we're going to test this one. All right, here's what my test would look like. It's actually not that bad. Don't worry. This is 1/2 squared. This is 1/4. This is 1/2 squared. It's negative 1/2 squared, which is also positive 1/4. And then this is negative 7.5 plus 5. That's negative 5 on 2. That's negative 2.5. Okay? So I have one negative multiplying 2 positives. We're still negative in that region, just like our picture predicted. Okay, so make your connections to your pictures. In this region, we're bouncing again. We can look at f at minus 6. Okay, f at minus 6 here returns minus 6 plus 8 is 2. 2 squared is 4. Minus 6 plus 7 is minus 1. Is positive 1. Positive 1 squared is 1. And minus 1 plus 5 is negative 1. So we can see that that's negative through there. Okay? So we're negative in here, and then we're going to be positive over here. Let's test f at 0, because that's the easiest one to check. Okay, it's actually not that easy. Easier would be f at -6. Sorry, -4. Let's test f at -4. It's just giving me easier numbers to check. 0 is not always easiest. -4. It's still in that region. Okay? -4 plus 8 is 4 squared. -4 plus 5 is we're multiplying by 1. And -4 plus 7 is 3, but we square it. So that is in fact equal to 144, my favorite number, but positive. Okay, so it's not bad. That's like up there. It's actually swings, goes up real fast, eh? It was 0 at f at -5, and it's already 144 at -4. So in the space of 1 unit, it changed. It's like first difference is plus 144. It's gross. Okay, so now we know this. So now we want to know when this is true. So we could have x is equal to -8, comma -7, or x is greater than or equal to -5. These are our regions where this thing is greater than or equal to 0. Questions about this one? No? Fairly straightforward? It's cool. Careful with your bounce roots. With your even roots, when you're inputting your factors in there, you want to make sure those are always positive. Something to the power 4 is always positive. Something to the power 6 is always positive. Something to the power 2 is always positive. Or 0. Okay. So, again, same thing. I mean, doesn't change very much. We're going to skip that example. Let's do this example. Okay. So this one is a little meaty. So we are going to tidy up our algebra a little bit with our inverse operations pen. I'm going to take away x squared, take away 3x, and add 1 to each side so that I set this thing equal to 0. And then I get this lovely cubic expression, f of x is equal to 2x cubed minus 3x squared, plus 3x squared, minus 8x plus 1. Okay? And so I'm looking at that and I'm like, ooh, 1 almost works, but not quite. Darn, I'm a little disappointed. How about minus 1? Minus 1 gives us minus 2. Plus 3 is minus 1. Plus 8, no. Doesn't work. Sorry? Plus 3, yeah, right, thanks. That was going to become a real problem in just a second. Plus 3. So now we have to test plus and minus 3 because we're looking at possible factors of this one. So let's see. If we have x as 3, then we have minus 24 here as our only negative. Here we have way bigger than that. So that's not working. Way bigger than that. But then this one is still also big. So let's try negative 3. So with negative 3, f at negative 3 will give us 2 times negative 27 plus 3 times 3, which is 27, plus 24 plus 3, and we can see that that works. Okay, there's 27, there's another 27, there's negative 2 27s, that's equal to 0. Okay, that's all rough work in my mind. So we know that f at minus 3 works, and my suspicion is that the other two roots are both like are funky. So let's see. So we're going to divide by x plus 3 because we found f at minus 3 was 0. So divide that into our 2x cubed. Oh, and this is also less than or equal to 0. That's important to keep. Okay, 2x cubed plus 3x squared minus 8x plus 3. We divide it in. Multiply by 2x squared. Subtract 3x squared, but it's negative, minus 8x. So we will be multiplying here by 3. So we have minus 3, not plus. Minus 3x. Multiply that by this, gives us minus 3x squared minus 9x. You put that in brackets and subtract it to make sure that that goes away. And that minus 9 becomes plus 9, and that gives you positive x plus 3. And isn't that nice to see? We have a plus 1 there. So we want to multiply to 2 and add to... Why did I miss that? I should have found that root. Oh, it's because I had 3 there. Yeah, so 1 worked. Yeah, 1 of course worked earlier because I had minus 1 and not minus 3. So that was interesting. Now we're going to factor this one. So I can see that that's the same thing as saying 2x squared minus 2x minus x plus 1. That factors by grouping as 2x times x minus 2. And then, x minus 1, not minus 2. And minus 1 times x minus 1. And that gives you 2x minus 1 multiplied by x minus 1. Very good. So there's our fully factored quadratic. So that is to say 2x minus 1 multiplied by x minus 1 multiplied by x plus 3 wants to be greater than or equal to 0. All right. Now we can build our number line, which is, again, rough work. We're going to build that out. We have minus 3 over here. We have 1. And we have, 1/2. So let's make that 1/2 and 1. Okay? So now, let's test some values. If we have, and you can test here, or you can test here, wherever you think it's easier. I think it's easier to check in the factorized version, so I'm going to switch to blue and check f at minus 10. So as we're coming up towards infinity, 2 times minus 10 is minus 20. Minus 20 minus 1 is minus 21. This is minus 11. And this is minus 7. We are multiplying 3 negative things together, so that will certainly be negative in that interval. Next, I'm going to check 0. F at 0 is nice. Okay, so here I have minus 1 times minus 1 times 3. That's going to be positive in that interval. And then in this interval between 1/2 and 1, so there I have to choose something funky. So let's choose 3/4. So f at 3/4. Okay, 2 times 3/4 is 3/2. 3/2 minus 1 is 1/2. 3/4 minus 1 is minus 1/4. And 3/4 plus 3 is 3 3/4. So it's not that bad. It gives you good fraction practice. I have 1 negative in there. I am clearly negative. And then after 1, let's test f at 2. 2 is fine. So f at 2 we'll test. And then we get 4 minus 1 is 3. 2 minus 1 is 1. 2 plus 3 is 5. We're positive times a positive times a positive, so we're positive there. Great. So that is to say our values where this thing is greater than or equal to 0 are between here and here inclusive and after there. So we're in there and after there. So I can write that in interval notation as, inclusive bracket, please, square bracket, inclusive bracket. Okay, minus 3 to 1/2, and the bracket, union, inclusive bracket 1, exclusive bracket infinity, because we never include infinity. Okay, so that would be a way of representing that one. Keep going. Questions here? All right, let's go. I wanted to do the this one. The price P in dollars of a stock T years after the stock opened can be modeled by this function given below. I'll circle back to the other examples tomorrow to split up the lesson. So that, oh my goodness, yeah, we did a quiz today, so we're a little tight. So actually, I'll do this one tomorrow. We'll pick these up, these examples up tomorrow. Just looking at the time. The Delta Math has been posted for today, and textbook practice is all right there. If you feel underprepared for any of the examples, know that I will be covering some of these examples tomorrow, right at the start of class. Okay, thanks very much, everyone.